All right, good morning, everyone. I hope you're doing fine and ready for day 22. We are going to talk about automated fiber placement process planning today. And we're gearing up in almost 1 week from today. It will be the wrap of this awesome month together. Good morning to Piyush, to Venkatesan. Good morning to everyone. And thank you for joining this morning. Hello, Marty. All right, awesome, awesome, awesome. Let's give it a minute, a quick minute before we go ahead and get started. Good morning, Omran. So the way this is going to happen today, it might be a little bit longer than usual. So we usually stick to like 20-ish minutes. At one point, if technology is on our side, I will be playing a recorded video at the end, relevant to some of the exciting research that I do. Actually, AFP process planning, that is really the core, the heart of my research. Before I go ahead and get started, process planning is actually the matchmaking between design and manufacturing. If you are not familiar with the terminology, when we say process planning, we're talking about the individual that has the nightmare of coordinating between what the designer is thinking and what are the manufacturing capacities. Oftentimes, we have an issue. Oftentimes, what we have is somebody that is sitting and doing their design and not aware of the manufacturing knowledge. And this creates a problem because you can create a design, and that design of yours can be a little bit unmanufacturable, or as I say, sometimes it can be manufactured, but at a highly required cost. So let's go ahead and get started. Steve, Aporv, I'm glad that you guys joined us this morning, and let's get started. So when it comes to AFP process planning, today what we're talking about is how do we think about manufacturing this composite, this tool path. When we're using these tools and we are using the methods that we need to coordinate between design and manufacturing, how can we prevent some of these issues? Sometimes what you can have is you can come up with a certain design and it meets your requirements. However, it meets the requirements, but you have an issue when it comes to manufacturing. So process planning requires a lot of definition of the layout strategy, of the tool paths, of the process parameters, and we're going to talk about that in detail. Go ahead and let me know if the voice is good on the chat. Let me know that this is working well. Elio, Nick, Mithun, and Katrina, I'm glad you guys joined. All right. So, all right, perfect. I see some folks saying good evening. So yes, this is the world. So I picked the time 12 Eastern because that would be 9 a.m. California, and that would be all the way to like it would cover most of the world. So this is why I picked this time. And actually, I would like your comment on the time of this meeting because when this month ends, I'm going to be doing a weekly update. So it will be an hour long every week. And I was thinking on Wednesdays. So let me know when you think that we should be the time. So please let me know. So let's get started with our topic and in detail. So layup strategies, and this is what we are delving into. It's all about coverage. It's all about how you tell the machine it has to move in order to cover the whole spectrum of your design. If your design is something like this water bottle and you want to cover this area, you're going to face the issue of, as we talked about it several times now, that the toes are going to have, you're going to have to think how you want to cover it. If let's say you're covering a 45 degree on this water bottle, how would you ensure that, look, I'm doing a 45 degree, look at the bump, at the wrinkle, if you remember AFP defects. So we talk about the layup strategy and we talk about coverage strategy. So what does this mean? This will be very clear at the end of today's lecture. So let's start talking about different concepts. Fixed angle. So this is when you, in geometry, you take what you want to manufacture. You say you want to manufacture a 45 degree. You put a plane in this 45 degree with respect to your 0 degree reference, and the intersection between the tool and the plane would be your curve. So this is an example of a constant angle curve. The fiber angle does not change. You don't have any deviation, but it can be a little bit problematic because what can happen is you can end up having something that has a lot of steering. So this is an example of the constant angle. Now, sometimes constant angle doesn't work, so we came up with a constant curvature. So basically, this constant curvature is when you are trying to, instead of having the constant angle, you have you set up the geometrical property of curvature. So it's a little bit a mid-plane between two different elements. The third one is reference curves. So the geodesic path. So take a look at this, and this is a very good example. By the way, on LinkedIn, on the archive page, what I did is, so this is a major state of the art that my research team has done. And all of these pictures are from different publications. All of them and the proper citations can be seen in this paper. And on the archive page, I actually already placed the link where you can click and go into this 32-page document. What is it that I'm talking on in here? If you're still lost and confused, take a look at this graph. And let's explain it once again. So this is your constant angle. You see the black curve that you have in here. This is the cone that you wanted to cover. And if you have done the constant angle, so as it's moving, the machine, the fiber is still in its constant angle, you would have this curve. This curve, while you will not have angle deviations and you will have your design of 45 degrees, however, it will have a lot of steering. As you can see in here, the angle, and this is the projection, just so like you're looking at top view, you can see that you have like you're forcing the toe to do steering. What do we know about steering? We talked about it several times. The moment you start forcing steering, you're gonna have a lift of the toe. So you're gonna have issues such as wrinkles and whatnot. Now, then we thought about, all right, let's do the path of least resistance, geodesic. Geodesic simply means between 2 points, you take a straight line, like a bird's flying. So we take the shortest path and we get with geodesic, but that prevents you from having the flexibility of composites and from having the flexibility to actually tailor things. This is where constant curvature, the one that you see in red. So whereas the geodesic is this one in green, whereas the constant angle is this one in black, the constant curvature is this one in red, which is somewhere in between. It's a trade-off between having your angles the way that you want them and having steering and puckers and defects in here. Now, all of this is for fixed strategies. You want to have a strategy and that is it. But then comes along the concept where you can have not a constant angle or a fixed angle, but a variable angle. So you would be steering. You would take something and you say, so let's imagine the case together. Let's imagine that this part is going to withstand a force from this orientation and a force from this orientation. What you can do is you can tailor, just like a flow, the tool path between these 2 points. So you can start having some kind of what we call steering, and you can create what we call variable stiffness laminates. So you optimize your path based on the optimal structural performance. All right, so let's go ahead and start with the first question for the day. Which reference curve would you use to limit steering? So which one, if you remember, as we have described it a little bit before, we talked about 4 elements. We talked about constant or fixed angle. We talked about variable angles, constant curvature, and geodesic. which one you think will not have any steering or any puckers if you wanted to minimize this defect? All right, let's go ahead and see your answers. And I did get a funny phone call, so it stopped my LinkedIn. So now I can see. All right, so all right, Apoorv, I see you answered D. Miguel, you answered D. Let's see some of wow, you answered D. All right, it is very clear that you guys got it. The geodesic pass is the right one. And if you take a look into it again, the geodesic pass is a straight line between 2 points. So this is the one that will minimize the steering. What we really want is the constant angle. We can't have that because of the excessive steering that it can happen. Then we move on to geodesic, but then it limits it so much. This is why constant curvature is somewhere in between. But once again, based on your application, this is how you decide what you need. All right, now what we have done is half the battle. You have decided how you're going to create a reference curve to start your manufacturing. But how are you going to propagate that? So when you have to cover a whole surface, having one curve is not enough, because there are two methods that you can do. You can either take the curve and start offsetting it, or you can take the curve and start shifting it. And these are two different techniques. Let's understand what they are, and then let's understand the issues that we can have from each one of them. The first one is the offset curve. As you can see in here, what we do is we take a path and we take the normal to the path and we construct a new path. So what is happening in here? Take a look at it. The curve and the analysis of your curve has changed when you offset it, because with every offset, you're gonna get a new curve. With every offset, look at this in here, this one becomes this one becomes this one, and so on. So what can happen is a relaxed angle that you can have in here suddenly becomes a very strong steering angle that can cause problems, because it's one thing to try to steer along a, what is this, 3 inches? It's one thing to try to orient along 3 inches. But as I'm moving forward, imagine now this location and you're steering along it, and suddenly you're gonna have a major pucker. So this is the offset curve. Now, the other alternative would be to shift the curve. So as you can see from here, along the orientation, all we do is we take the curve and we shift it. But what will happen is when you do that, because you're not gonna have a complete adherence. So the offset curve, you're making sure every point where it ends, there is another toe. For this one, you're not making sure of that. So it's gonna create gaps between those shifted curves, and it can be problematic. So it's a trade-off. What you want? Do I accept gaps and overlaps? And like this, I would go more of towards the shifted strategy, or you want to minimize your steering and so on, or you accept the steering like what we have in the offset, and you want a full coverage. So I'm going to say this one more time. In an offset curve, you would have like going towards zero, minimizing gaps and overlaps, but you will have excessive steering. In a shifted curve, you will not have more steering than what you've originally planned in your reference curve, but it will create for you gaps and overlaps between them. Now, there are other types of strategies, such as independent curves. So you can actually try to say, you know what, I am not going to create one continuous one, I'll create short independent courses. Whereas this is a good coverage strategy, however, designers will hate you, because the whole goal of using composites is try to keep it as long as possible so that it can carry the load and disseminate it along the lengths. So making the fibers shorter, you are actually influencing the design, and you are not getting what we want. All right, so true or false? When using the shifted curve coverage strategy, so this is once again the shifted curve. You take the same curve and you shift it. So you're not changing your steering, but you're accepting gaps and overlaps. So when using the shifted curves coverage strategy on a complex part, the fiber direction of offset parts are not guaranteed. Do you think that is true? Do we look at this once again? Are we changing the fiber directions from the original path? Is there anything changing or not? So go ahead, answer true or false. All right, let me see some answers. I see that the time is suitable. It's 9 a.m. in San Diego, 9 p.m. in India, 7 p.m. in Greece. Hello, Katrina. I have an aunt that I love that lives in Greece. All right, so hello, Hassan. I see the answer is I'm trying to see people answering false, and this means that this is are not guaranteed. So this should have been false. So this is a little, I agree with everyone. This should have been false, and we will correct that. All right, cool. So now moving on to CAP optimizes the layup using these strategies. So this is this piece of software that we have created. And this is a piece of software that we have done here at the University of South Carolina. And I have prepared a video for it, and we will be looking at the video together. This is the software that was done by Joshua Halbritter, that is my student. So let's see if the video will be playing. So I'm gonna play the video and come back from this slide, crossing fingers that this will work. So the first thing is I'm turning off the slides, and I'm gonna put the video, and it goes. Let's see if it works. Please let me know as the video starts playing. Let me know if you have good sound and it's working well. So I did tell you it's going to be a little bit longer than usual because there is a demonstration for the video. I am not going to play this video is 20 minutes. I'm going to be playing approximately 7-8 minutes of the video, but I'm going to be posting the full video on my LinkedIn later today. And let me know when actually it is working.
My name is Rami Harik. I'm an associate professor at the University of South Carolina and a resident researcher at the McNair Center. This video talks about our work on computer-aided process planning that we conducted in the 2C22 CRT. Process planning is the matchmaking between design and manufacturing. Using a computer-aided process planning tool, we will help alleviate some of the consuming time and to reduce some of the complexity that a process planner undergoes when he sits in front of a design and he's trying to match the optimal manufacturing process. We focused specifically on two elements, which are two of the most common functions: the starting point selection that will be used to actually compute the manufacturing toolpath, as well as which layup strategy would be optimal to use to obtain that optimal manufacturing plan. The software that we've built tried to mimic the process planner and how he would think when he faces a certain design. Before we reached the stage, what we did was an extensive survey that we sent out to all of our CRT partners, which resulted in 16 different process planning functions that are important. They were classified into 3 subgroups. The first one relevant to process optimization, the second one relevant to toolpath optimization, and the third one relevant, miscellaneous, relevant to several functions. All the data about the survey is available in one of our SAMPI papers. The software that we developed tries to integrate the influence of the individual process planners. In the first stage, in Major 1, we compute the main attributes that are needed in order to make the assessment. We take a look into gaps, we take a look into overlaps, we take a look into angle deviation, we take a look into steering violations, and we actually take a look at each one of those 4 features from 2 perspectives, the instance and the severity. The concept behind that is sometimes you have a major gap at a certain location, and that deserves a different kind of treatment than having a combination of several gaps at other locations. In brief, the tool enables the process planner to minimize time and to take some of these important functions that will help obtaining composites and manufacturing composites at a faster rate, leading to a faster certification cycle. My student, Joshua Halbretter, will be taking an example and will be going through all the details of that example so that it clarifies how the process planner actually behaves, what is the capability. The University of South Carolina worked closely with the OEMs to test and to validate the results of the prototype software of the process planner.
So we're going to begin with starting the CAT module. So this is will be the starting point once you have the boundaries and triangles defined along with your tool surface. The first thing you're going to do is open the CATIA laminate, which contains the ply boundaries. I'll go through and open that here. And then the next step is to open your tool surface that you're going to be using. So now, after this open dialog is complete, we open up to our surface and ply boundaries, and we can go through and look through them right here in our little laminate tree. And so the next operation will be selecting our plies of interest from the laminate tree, right-clicking, and finding the surface centers. So as we can see, we've generated a couple of centers for each of these ply boundaries, and we can investigate those by clicking through the laminate tree. And the next step going forward will be exporting the batch file containing these scenarios to VCP. And then we'll just generate the thickness. Turn that off. And now the benefit of the batch file is that everything will have been generated and imported automatically. So ply angles are predefined. The scenarios are sorted by their ply that they're being generated for. And if we actually check out one of these scenarios and we go to the Generate tab, you can see that it's already selected the ply boundary definition from the CAD model along with the specific starting point on the surface. So all of our work for that point is already done by the CAT module from generating that batch file. So the next step will be going into the batch manager from the initial page. And I already have the batch process set up, so this is where you actually select the individual processes that will be performed during the entire batch processing. And I'll just run you through those. So the actions we have is it will generate the course for each of the plies as we have defined them from the batch file. It'll export gap and overlap reports, so this will define the size of each of these gaps and overlaps. The laser inspection data is helpful for visualizing these gaps and overlaps back in the CAT module. And the FEA will include the data for the overlaps and steering. Or for the FEA file will contain the data for the steering and the angle deviations. So now that we have that, we just need to go make sure it's generating in the correct directory. So we need to use export laminate structure. Using the laminate structure, that's fine as default. We will select the location. So we'll go through on our desktop, find back our laminate file that we generated. We'll select the name of that directory. And then we will go through and select the centroids file that we generated because it'll be updating that as we're performing the batch. And the final step would be going through and highlighting all of the scenarios that we've generated, select nodes for batch processing, and starting the batch. Now this is going to run for each of these scenarios that we've generated and export the results to the directory. So I'll go check out the results that we've generated. You can see for ply 1 and 8. So we skipped one for sake of time. I'll go check out these so we can see that we have the results for each of these scenarios. We actually need to move this back over into this analysis file, just like that, and now we're fine to re-import things back into the CAP module. So we'll do that by check for VCP output. So this will ask us to go select the folder containing this information. So we'll go to our laminate file, dig down into that, and this is the file that we just generated with all the analysis data. We'll go ahead and open it, and we will watch it import. All right, and now that we have our analysis result imported back in, we can go and begin to investigate the three majors that we have included with the software. So we'll begin with looking at the first scenario, just for an example, and we can go through and look over here at major 1. So the big first thing we can look at are the histograms that are generated for our data. So this is going to show you increments of within the data, or subsections, and it'll tell you how many defects occur within this certain range. And so you can see we have primarily angle deviation and overlaps that are generated for this scenario. We can actually go through and begin to check these out. So here we have the overlaps. You can see that they are up towards the top of the surface. Now we can check out the ability to begin thresholding these. So what your thresholding is doing is it's basically setting an allowable minimum or maximum for the defects as they occur. So we can go and begin to threshold these with this tab. So now that we're thresholding, we can see as we're selecting the different defects as they occur over here within the ply boundary. And the same can be performed for the angle deviation. And what this is doing, these two bars represent the threshold for the instances and the severity. So we'll just run through a quick definition of these. Instances are how many of these defects occur across the surface. So if you have a huge number of defects but they're very small, you don't have a huge impact, and that's what this initial threshold is for. So you can cut those out if you're interested. And moving it all the way to the top will reduce the measurement, and allowing more increases the measurement. And moving into severity. Severity is how significant are these defects? Are they a significant portion of the surface, or are they smaller and less significant? So you'll be these defects won't be impacting your overall strength margins. So we can see that we can go through and threshold both of these. And the same is true for the angle deviation. And now that we have scores for each of these, we can move ahead and go into major 2. So this is where you're actually beginning to prioritize these set of defects. So for now, we only have overlaps and angle deviation, so we'll be primarily looking at these two sections. So this is the AHP matrix, which stands for Analytical Hierarchy Process. So this allows you to do kind of a one-to-one comparison of each of the defects and their type as they occur on the surface. So you can do severity and instances for each of these. And for now, we're just going to be using the defaults that we've included. So we'll just run through those real quick. So you can see coverage is prioritizing the gaps and overlaps, varieties. Fiber angle prioritizes the angle deviation, and fiber steering is prioritizing the instance or the steering. And this will combine with the measurements that were generated in Major 1 to control the scores that are generated for this scenario. And so now into Major 3, we can see where these measurements and rankings are combined to generate a score for each of the scenarios. And in the tree we have, or in the table we have the set of layup strategies and the starting points. And so now the scope of the table is dependent on the selection of the laminate tree. So we can go through and select each one of these. And we can see we have a set of scores that are generated in the layups tab, or in the Major 3 table. And so now our next step will be processing these, so we can actually begin to generate the next set of scenarios to perform the next step of iteration. And we'll be focusing on ply 8 for this part of the demonstration. And now that we've scored our data, we can go through and we will show you how to generate the final export. So this is the one that's going to select the best scenario from each of your plies that you generated by choosing the lowest score. So that means it had the lowest amount of each of these measured defects. So we'll go through and select the final batch, and we will go through and investigate that. Now we can go through and see that it's generated the best scenario from ply number 8 with the best geometry and the best starting point. And now you can save it, and it would be ready for any further processing that you are interested in doing or moving into the manufacturing stage. That wraps up a short demonstration of a few iterations with the CAP module and VCP.
We have, first of all, created an extensive AFP defects database where any AFP defect, we can know information about its existence, its significance, its value, and what does it mean. That was the first groundwork. Then, after we have developed this AFP defects database, we actually created the standard functions for process planning, and we were able to identify 16 of them and to organize them into groups and priorities. And in the third part, we have taken 2 out of these 16 functions, and we have developed this software that we have presented to you today. The future transition path is we are looking into the continuation of this work, as well as to push it and to push the boundary of automation of process planning.
All right, so that worked very well. Technology was on our side today. Let's go ahead and wrap the lecture. So once you're done with this and you have created your optimal manufacturing strategy, we proceed with verifying on a programming software if this is functional, such as VCP. This is something that we're going to cover and talk about in the upcoming couple of days. And finally, this is a summary of what we've done. Process planning can help you understand the matchmaking between design and manufacturing. We use reference curves and coverage strategy, and process parameter selection is dependent on material and hardware and all of these different elements. Talk to you tomorrow. I hope this was a good lecture. I hope you liked it and enjoyed it. And you enjoyed the little video from my research team. Thank you so much, and see you tomorrow for day number 23.